really concentrated in this area. If you look then on this proliferation issue, what happened, this is a timeline going up to fairly recently, and it shows the number of petawatt class systems that are operational. You can see that they've taken off since 2005. In the US, they reached a certain level around 2011 and flatlined, and there's been no increase since then. There's a total of 9 petawatt class lasers in the US. Going around 2012 or so, that number was overtaken in Asia, and the real growth has been in Europe. Since 2014, there's been a very substantial growth in petawatt class systems outside of the US. Here's the interesting point, though. Even though the actual install base of petawatt class lasers has moved to Europe and outside of the US to Asia, as a country, we are still doing, I claim, the most advanced petawatt class systems. Konstantin Hefner here is from Livermore and was leading the group that has made what's called the so-called Happel's Ti-Sapphire laser. What's interesting about it is instead of flash lamps, it's got an enormous array of semiconductor lasers. I think this is the largest array of semiconductor lasers made. It's 800 kilowatts. What it has enabled is operating at much higher pulse rates, 10 shots a second. That's a factor of 10 at least over what's available. There's some other clever uses of technology as well as gas-cooled laser media. And this derives from work that was done in the fusion area to try to get a rep-rate fusion driver. Very nice system. National Energetics, Todd Dittmeyer's in the audience, has followed on with the glass development, is now working to ship a 10 petawatt glass laser. Todd has managed to work with OPCPA drivers to bring the pulse width down from the original roughly 500 femtoseconds in the first petawatt laser down to 150. So that means now with not much more laser than the first petawatt laser made at Livermore, he can get to 10 petawatts. The other interesting part, and this, by the way, there's some techniques of mixed glass amplifiers allowing this. The other thing he's doing is water cooling discs, or they are doing, I should say, to get the rate of a shot a minute. So again, this is the most advanced technology, and it's being shipped to the Eli Beamlines facility in Prague. And these are the systems, these are where these are going. And this is, in some ways, these pictures are the kind of the warning to the community in the US of what's happening in the rest of the world. The Eli facilities are under construction in Prague, in Romania, and in Hungary. The 2 key lasers in this facility out of 4 will be made in the US, and they're the best performing lasers. In the system in Romania, the French company Thales is building 2 10 petawatt lasers. Those will hold the record for peak power once they're commissioned. And there are a whole bunch of lasers going into Hungary, but they're all from the EU. This Eli Facilities was built as an infrastructure improvement in Europe. The total investment was about 800 billion euros. That works out to, and they'll have about 10 petawatt class lasers. It works out to about 80 to 100 million per laser. It's not that big of an investment, but it's all over in Europe. So what's going on in terms of the near future? While the US has developed this technology and we can still make the cutting edge of the systems, the newest systems are being installed outside of the US. The current record holder for high peak power is actually a Ti-Sapphire laser in Shanghai. And after I'm finished, we're going to have a video from Ruxin Li, who's leading the group in Shanghai that did this. 10 petawatt class lasers are being built by a French company, and a 100 petawatt class laser has been approved for construction in China. So, and there are no petawatt class lasers under construction in US facilities. So we had an early lead, we developed a technology, we then started shipping it overseas, it proliferated. Now the newest technology is being shared amongst many countries, and the really record-setting lasers are not in the US. So here's a possible future, and part of this will come about if the US decides it really wants to invest in the technology. There's lots of stuff that still could be done. Livermore has led the way in replacing a very old technology of flash lamps with diode lasers. And this is more than just a rep rate issue. It's going to allow feedback control systems that will improve not only the productivity of the science being done, but also the quality of the focus and also the statistics and experimental work, and that's starting. You can go to directly diode pump lasers. That requires some advancement in materials, but that could lead to even higher pulse rates and efficiency. And these technologies will be needed for way in the future when we want to make TeV class accelerators. Beam combined fiber lasers are a gleam in the eye of a number of people, and there are some substantial challenges in doing it, but they could also be a game changer. You do have to find a way to get 30,000 lasers to all work coherently. There's some work done in short pulse OPCPA systems that go below the standard 20 to 30 femtoseconds, get to about a femtosecond. Now you can have really tabletop petawatt lasers because you need now 30 times less energy. And then finally, X-ray free electron lasers, Phil will say, their only problem is their high cost, but they can get to very high intensities as well. And the US has strengths in all these technical areas, and a lot of it is, especially in the higher pulse rates, in investments not in petawatt class lasers by the Department of Defense, but in high average power lasers. There is certainly a lot of work in high power systems for directed energy, but it's just a different class of laser. So now let's see, remind me what your question was so I can see if I could answer it.
The question was the impact on the private sector and the benefits of the innovation that we would see commercially as we move forward with the development of these next technologies.
I mean, and one of the issues the report raises is the whole infrastructure in the US about building high-intensity lasers. As you can see, these facilities being set up in Europe, some commissioned with US lasers, but some with European-built lasers. You're going to be training a load of, say, 500 graduate students in Europe used to using those lasers. Some will go off and start companies. Now, if there are no facilities being built in the US, we're not employing necessarily US companies in doing this. You can imagine that what it took for EU funds to come to the US. It happened. I'm sure Todd can explain what was necessary to make that happen. It wasn't necessarily the easiest thing. That won't happen all the time, and it's certainly not happening in China. So the long term is, unless the US, my feeling is, unless the US invests in infrastructure here, we're not going to see commercial companies going into this area. And maybe that's fine, because there's about $1 billion of business in say, ultra-fast high sapphire lasers for medical applications. And frankly, US companies have seen that market as much bigger as the petawatt. And the petawatt, the issue is, I guess, in the future, the cutting edge of laser technology is these petawatt class systems. If we're not doing it, other countries will. Eventually, that'll have an impact on the infrastructure.
Okay, well, maybe we can explore this later on in the Q&A period too.
Sure.
Thank you very much, Peter.
Yeah. Now, I think I'll introduce Ruxin Lee. He's leading a group in Shanghai that has pioneered ultra-fast technology and high-intensity technology. He's built the largest, right now, high-peak power system, and he's going to tell you in this slide about where Chinese are going.